and same for the inductor. Today we'll see the initial conditions. Okay, the initial condition. Initial condition for inductor and capacitors. Okay, as we discussed earlier, the voltage across the capacitor does not change abruptly. Okay, similarly the current in the inductor does not change abruptly or instantaneously. Okay, like the initial current is I and the capacitor voltage is suppose Vc. So this voltage will not change immediately. What I mean is, suppose for example you have 5 volt across capacitor. Okay, now from the outer circuitry you are applying 10 volt across it. 10 volt across it. So this 10 will not come directly to this capacitor. The capacitor will oppose the change in voltage. The capacitor will oppose the change in voltage. Similarly, if we are having 5 ampere current flowing in the inductor, now suddenly you are applying this inductor with 10 ampere. So see this 5 ampere current will not change instantly. Okay, it will oppose. So the inductor is opposing the change in current and the capacitor is opposing the change in voltage. So up to what time they oppose it? Okay, this is the point. Okay, for very small time they will oppose, then they will allow to change in voltage and current. Okay, so see, I'll show this thing with timeline. Let me select the color also over here. Wait. See friends, suppose on the number line, this is the number line. Okay, here I'm taking t equal to 0. This is the time t equal to 0. What this indicates? This indicates, suppose you are having circuit. Here in this circuit, this is 50 volt given. Here we have switch. Okay, and this is the manual switch. We can close it, we can open it anytime. Here you have capacitor whose capacitance is given C Faraday. Okay, now the point is, initially it is charged. Let's take Vc as the voltage across capacitor. Now at t equal to 0 we are closing it or we can open it. It's depend on the requirement. Okay, either we can close it or we can open it. But at t equal to 0 we are doing. Means at t equal to 0 we are changing the conditions or we are changing the situation across the capacitor. Okay, means before t equal to 0, where is the time? Here is the time before t equal to 0. After t equal to 0, the time is like this. So the change is occurring at t equal to 0. Is it? So before t equal to 0, can I say this is the t minus? And can I say this is the t plus? Can I say like this? T minus means the time just before the 0. T plus is the time just after the 0. And please focus on the word just before. Just before and after. Means I'm talking, if this is the t equal to 0, so t plus plus means this is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 kind of thing. It's almost 0. This is limit kind of thing. I'm talking at t equal to 0 only. But at t equal to 0, if my phase will be in this direction, I'll say I'm looking to t plus. If my phase will be in this direction, I'll say I'm looking for t minus. Okay. So this initial condition theory is completely based on the t equal to 0 only. Okay. So t plus means very small amount of time. So for this small amount of time, the capacitor and inductor, they oppose the change in current change in voltage and current respectively. Okay, this is nothing but the initial condition. What it says, the initial condition says, suppose for this example we have taken the voltage VC across the capacitor. Just assume the VC is 5 volt. Just assume it. This is the VC, assume 5 volt. At t equal to 0, you are changing it. Means in this timeline up to here you are having 5 volt before this line. Before you switch it or you close the switch, the voltage across the capacitor is given as 5 volt. After this, after some time it will be changed up to 50. Why? Because at t equal to 0 you are closing the switch. At t equal to 0, at the specific point of time t equal to 0, you are closing the switch. Now capacitor will start to charge again up to 50 volt. But I am telling you the capacitor is not going to change directly the voltage across it. It will oppose. Up to what time it will oppose? This is nothing but the initial condition. And what I am saying is if minus, I'm taking this minus 0.000000001 is the time left to the t equal to 0, and this is the time right to the 0, and this is exact t equal to 0. Okay, so I'll ask you one question. What is the value of voltage across the capacitor at this time? Yes, this is the 5. This is the 5 volt, because till now you didn't close the switch. Now at t equal to 0 you are closing the switch. Now tell me the situation. Tell me the voltage across the capacitor. Is it 50? No. Capacitor will oppose it. Up to what time? This much of time it will oppose. Up to 0.00 for a very little time the capacitor will oppose the change in voltage. So up to this time the voltage will remain 5 volt. Will remain 5 volt. Is it okay or not? So can I say if this is VC 0 minus, see, I told you earlier I'm talking at t equal to 0 only, but 0 minus means just before t equal to 0, and here 0 plus means just after t equal to 0, and I told you VC 0 minus is the voltage before switch closed, and VC 0 plus is the voltage after switch is closed. So these two are the equal. 0 minus is nothing but 0 plus. This is the property of capacitor, that capacitor will not, across the capacitor we can't change the voltage directly or instantly. It will take some time. Okay, so for this range I can say this is 0, this is 0 minus, this is 0 plus. Up to this range voltage is not going to change, or I can say in other words, up to this much of time only the capacitor will remain constant. Whatever quantity it has, whatever voltage it has, it will be a constant. Okay, so this is about the capacitor. But instead of capacitor, if now you have inductor. Now instead of capacitor you have inductor. See this. We are applying the current, take current 10 ampere. Initially I'm just taking it. Initially suppose 5 ampere current is flowing. At t equal to 0 you are closing it. Okay, again come to the timeline over here. This is t equal to 0. This is just before t equal to 0 means 0 minus. This is just after to t equal to 0. So 0 plus I'm taking. Now at t equal to 0 we are closing the switch. We are closing the switch. Before t equal to 0, in this region, the current across inductor is 5 ampere. At t equal to 0, you are closing the switch. Does it change directly or instantly? No. Up to what time? Up to this time. At t equal to 0 also, the current into the inductor will be 5 ampere. After this it will change. Whatever current you are applying, that entire current will come to the inductor now. After this you are having 10 ampere. But before this you are having 5 ampere only. So in the timeline the end points are minus infinity and plus infinity. So this thing is called the steady state. Steady state. These both things are steady state. Steady state means the time at which the condition of capacitor or inductor is continuously at a constant. Means what I'm saying is, if the inductor is having 5 ampere current flowing for a long time, it means it comes into the steady state. Okay, so for a long time, suppose voltage or current is in the capacitor or inductor respectively, so we can say it is a steady state condition. I hope it's clear to you. Now for the inductor, the 0 minus current is equal to the 0 plus current. Is it okay? This is for the inductor. And for the capacitor, we see 0 minus is equal to 0 plus. This is for the capacitor. This is the initial condition. I hope you are getting it, right? So this is all about the concept. Now, see, come to the see, the capacitor will provide reactance, as we talked earlier about this also. Inductor will also provide this is inductor, okay, L. This is capacitor C across point A and B. So capacitor and inductors provide reactance into the circuit, not resistance. It's a reactance. The unit of the reactance is also ohm, the same thing. But for the capacitor and inductors, we call it the reactance. So the reactance provided by the capacitor, we call is the capacitive reactance, denoted by Xc. And the value of Xc is nothing but j omega c. Though this is the frequency dependent component, we talked earlier about this also. So the reactance, capacitive reactance is 1 divided by j omega c. Now come to the inductive reactance, XL. This is nothing but j omega L. This is nothing but the reactance. This is the reactance of the capacitor and this is the reactance of inductor. Okay. Now if you observe this carefully, now if you are having omega equal to 0, omega equal to 0 means frequency 0. For which current we are having 0 frequency? It's a DC current. So for the DC current, Xc will be 1 by J into 0 into C. Whatever the value of C having C, the overall value of Xc will be infinity. Infinity means open circuit. So can I say for the DC current, the capacitor reacts like an open circuit? Can I say this? Open circuit. For the DC current, the capacitor acts as a open circuit. Now come to the reactance, inductive reactance. The formula is j omega L. Now j omega is 0 because the DC frequency is 0. L, whatever the value of L has, I don't matter. The entire value is 0 ohm. 0 ohm means between 2 points you are having 0 resistance, means they are shorted. Open means between 2 points you don't have any resistance, means they are open. So short circuit is like this. Okay. Similarly, for this formula, if you will talk about in Laplace domain, so we know S equal to j omega. So in the Laplace domain you can write it Sc, and for this you can write Sl. Is it okay? Now we'll see the initial condition effect on the capacitor and the inductor. What I mean is, I'll show you here. You are having capacitor first. Okay, fine. Across point A and B, the value of capacitor is C. Okay. Now at t equal to 0 we are talking about. Time is 0, right? Now see, time is 0 means frequency S is infinity. Is it okay? This is the reciprocal. Time is the reciprocal of frequency, S is infinity, and the capacitor reactance Xc is 1 upon Sc. So at t equal to 0 I'm talking about. At t equal to 0, if time is 0, S is infinity. Okay. So I can say limit t tends to 0 of Xc. When I'll convert into S domain, so I can I write this S tends to infinity and something like this. See, what is the final value theorem? Can you apply over here? This is the S into XC, right? So this will become 1 by, oh, we will do it directly kind of thing. See, this is not proper. 1 by SC, here S is the infinity. So if you put infinity over here, we'll get 0. So can I say at t equal to 0, capacitor behaves short circuit. Okay. Similarly, for the inductor, if we'll see at t equal to 0, we know that inductor is nothing but SL. This is the inductive reactance. Okay. So at t equal to 0, it will be infinity, means it will be open circuit. What it means actually, whenever you are changing something, see, okay, I'll illustrate this thing in the numerical only. Come to the numerical now. We'll take one numerical and then we'll start and before that you should, revise this first. The inductive current is given by ILT is nothing but 1 by L integration T naught to T VL tau into d tau plus IL tau. This is nothing but the initial value. Okay. Initial value. Why? Because they stored the energy. Inductor and capacitor both stored the energy. So these things are also counting. Okay. Now come to the capacitor, and we have seen this already. We have done this. Now come to this formula or this question. Sorry. The problem is, assume that the capacitors are initially uncharged. These two capacitors are initially uncharged. Means V0 minus you are having 0 volt. V0 minus is given initially. Initially means before t equal to 0. They are discharged. Okay. Now at t equal to 0, we are applying something this. We are applying the current over here. Now he is asking, what is the V naught T? Where is the V naught T? Here is the V naught T. So how will solve this? See, to solve this circuit, we should know the capacitor equation, voltage equation first. The voltage across capacitor is nothing but 1 by C, 0 to T, here IC, dt plus V naught. This is the initial value of the voltage which we consider in the equation. We have seen it already, right? This is the initial stored energy, whatever it is. At t equal to 0, okay, you are applying some current, no problem at all. But before t equal to 0 also, it has something that will be carried out for some time. So we are adding this portion. Okay, this is the voltage equation. Now, to get the value of Vt or V naught T, what you need to take the value of ICT also. Where is the I is given? The current across C. This I is flowing in this circuit. The same I is flowing in the both of the capacitors. So this is IC, I can say. Now we are having IC. We have to break this time region in two parts. Why? Because we are having, see, here I am taking ICT for t equal to 0 to, this is the 1 and given in the second. So for t equal to 0 to 1 second, the value of the current is given is, this equation of this line is nothing but 60 t and given m, so 60 mt. This is the equation of this line. I think you know about this, right? So this is the current for this reason, and the current for 1 to 2 second. If you will find out the equation of this line, you will get 120 minus 60 mt again. This is your current equation. Now you got the current. Now your task is to find out the VCT. VCT is the voltage across 3 micro Farad, or you can get the same voltage for this formula for 6 micro Farad also. This is the universal formula for the voltage drop across capacitors. Now you can put the values of IC in this equation and you can find out the VCT, whatever he asks. So this is the VCT. I'm finding out 1 by C. Okay, fine. Tell me the value of C. This is the 3 micro. Micro is going up. It is the 10 to the power 6 by 3. Divide by 0. Because at 0 we are providing it. 0 to, tell me 0 to 1. 0 to 1. What is the IC? This is the IC. 0 to 1, the current is 60 MT dt plus the initial value of the voltage, and given in the circuit this is the 0. Okay, so this is the 0 volt. Now this milli will come out. So it will become 10 to the power 3 divided by 3 into this 60 will come out, and this will be t square by 2, 0 to 1. When you will simplify this, it will be, this is the 20, okay, and here I am taking, okay, so 10 to the power 3, 20 into 1 by 2. So 2 will cancel out, and it is 10 into 10 into 10 to the power 3 volt. This is the voltage across it. Okay. So the value of voltage here is, I'm taking over here, VT is nothing but, if we'll consider this T, so because he is asking in terms of T only, so instead of 1, I'll write the T only, T square, it will be 10 into 10 to the power 3 T square in terms of time T. Okay. This is the voltage across the capacitor in this region only. This is not the entire one, because we need to get the value of this one also. Okay. So I hope this is clear to you. Up to here it's clear. Now come to the second one. Now this VCT is again 1 by C. The formula is 0 to T ICT dt plus initial value. Okay. So for this reason, now I'm taking this for the reason 1 to 2. Okay. Second. So 1 by C. What is the C over here? 3 micro, 10 to the power 6 will go out. 0 to T. Now friends, please try to understand. Here the value is 1. Here the value is 2. Okay. Here ICT dt. What about this initial value? Where the capacitor current is going to change at t equal to 1, right? T equal to 1. So before 1, it was the initial condition. So initial, if they are changing at t equal to 1, so at t equal to 1 minus is the initial condition. So we have to check the value at t equal to 1. That is nothing but the initial value. So in the last voltage equation, we got it 10 into 10 to the power 3 into t square. I need the value of this at t equal to 1. So this is nothing but 10 to the power 3. So this is the 10 to the power 4 volt. Okay. So here the initial value is 10 to the power 4. I think it's okay to you. Now come here 10 to the power 6 by 3. 1, 2. You can take it 2 or t. In terms of t we need. Okay. But starting point is 1. The value is 120 minus 60 MT. Okay. dt plus 10 to the power 4. When you will solve this equation, you will get something like B. Okay. So your final answer is for this question, your final answer will be the voltage V naught T across the capacitor 3 micro Farad is 10 to the power 4 T square when T is 0 to 1, and whatever the value you got, B, T is 1 to 2. This is nothing but your answer for this question. I hope it's very clear to you. Now come to the second one. They're asking, obtain the equivalent capacitance of the network. Equivalent capacitance. See, if you will observe this circuit, the capacitors are not connected in series or parallel combinations. They are in, maybe they are in delta connection or star connection. I think now you can easily identify they are connected in delta or star. So to resolve this, we need to know the formula for the delta to star and star to delta. Okay. See, if you are having star connected elements, 3 elements, R1, R2 and R3. Now your task is to change it into the equivalent delta. Suppose this is delta over here which is this branch, and here this branch. Take it RA, this is RB and this is RC. Now we have seen the formula. The RA will be summation of this R1 and R2, R1 plus R2 plus multiplication R1 R2 divided by the remaining one, that is R3. This is the formula. But friends, here we are having the resistances, but in this equation or in this circuit we are having capacitors. So how to get the equivalent capacitance, or how to resolve the capacitance circuits and the circuits which contain delta and star connections? So instead of RA or instead of resistance, I'll take 1 by C. Whatever the value is, 1 by CA, 1 by CB, whatever it is. But instead of R, in the same formula, we'll take 1 by CA and something. Is it okay to you? So friends, I'll resolve this circuit. See, this 40, 30 and 10, they are connected in star connection. So I'll resolve this. I'll make it delta. Okay. So this branch will be here over here. Okay. Now we are going to resolve this. Just keep the formula in mind. Okay. Now we are going to apply. Now take the values of the capacitance. Suppose this is C1, this is C2 and this is C3. Now the value of C1, if you will calculate, the C1 is connected with 40 micro and 30 micro. And I told you, you will invert it. If you will write the equation, everything will be invert. 1 by C1 is nothing but 1 by 40 plus 1 by 30. Everything is in micro, this side and this side, so they will cancel out. So don't bother about that. This is 30 plus, in the next step, multiplication of both of them. 1 by 40 into 1 by 30 divide by the remaining one. The remaining one is nothing but 1 by 10. Is it clear to you? So come now. 1 by 40 plus 1 by 30 plus this 10 will go upside and it will be 120. Is it clear? This is nothing but 1 by C1. 1 by C1 is nothing but 120. You can take as the LCM. You can take 120 and this will be 3. This will be 4. This will be 1. 4, 3, 7 and this is 8. 8 by 120. Now you have to get the value of C1. C1 is nothing but 120 divided by 8. So this is 8 ones and 8. So this is in microfarad. So the value of C1 you got, that is the 15 microfarad. Okay. This is 15 microfarad. Okay, fine. What about this? I'll solve for this. Please remember this. Okay. Now I'll solve for the next one. Or, okay, fine. See, now the values are, suppose I have to take the C2. Now my question is to take the C2. 1 by C2. C2 is connected with 1 by 30, 1 by 10. This is 1 by 10, 1 by 30 plus multiply 1 by 10 and 30 both and divide by the remaining one. The remaining one is 1 by 40. So this is 1 by 10 plus 1 by 30 plus the 40 will go upside and it will be 10 into 30. Can cancel it out. you are having 1 by 10 plus 1 by 30 plus 4 by 30. Okay, take the LCM. 30 3 times, 1 times, 1 times. This is nothing but 1 by C2. Is it okay? So 4, 3, 7 and add. This is 30 by 8. Oh, sorry. This is 8 by 30. So C2 is nothing but 30 by 8. I hope it is clear to you. So C1 we got 15 micro. This is 30 by 8 micro. What about the remaining one? This C3. C3 I am calculating over here. C3 is connected with 1 by 40. 1 by 40 plus 1 by 10 plus multiply 1 by 40 and 1 by 10 divide by 1 by 30. 30 will go upside. This is 1 by 40 plus 1 by 10 plus 30 divided by 40 into 10. It will be cancelled out. Take 40 as an LCM 40. So it is 1 plus 4 plus 3. So finally you are having 4, 3, 7 and 8. This is the 5 micro. So now you are having 3 value. The resolved circuit you have. Okay. Let me clear it. Now the resolved circuit of this is, sorry, let me take the pen first. The resolved circuit is now, this is 50 micro. Okay, fine. This is the resultant, that is 15 micro. Okay. And this was connected over here now. So this 50 and this, they are in parallel combination. Fine. Now come to the 21. 20 microfarad is given, connected in parallel with this branch. This branch was some 30 by 8 and something. We got 30 by 8. Okay. And at last this branch. This branch was 5 micro. 5 micro. Now these two are in parallel combination. So resultant will be 65. We can add. If capacitors are connected in parallel condition, we can add them. Here also we can add. And then these two are in series combination. So again we apply the formula. Again the parallel combination. And here we can get the C equivalent. Okay. So I hope this one is also clear to you. Now come to this. The problem is in the circuit. This problem is given for this circuit. In the circuit 6 points, this one, let Is is given 30 e to the power minus 2t. And where is the Is? Over here. This is given 30 e to the power minus 2t. Okay, fine. Now V10 initial condition is given. Where is the V10? Here is the V10. V10 is given 50 volt. V20 also given. Here is the V20 and that is 20 volt. Now we have to determine V1t, V2t and in the second question the energy in each capacitor at t equal to 0.5 second. So our task is to find V1t and V2t. Okay, initial condition or initial values of the voltage across the capacitor is given. V1t or V10 is nothing but 50 volt. V20 is given as 20 volt. Okay, it's fine. Now the voltage equation across the capacitor is, the voltage equation across the capacitor is 1 by C 0 to t. Here ICT dt plus, tell me, initial value. Okay. So can we easily get the value of V1? Why? Because, so see, across this V1, the current is given already. Okay. Means if you are willing to calculate V1, you need to put the values in this formula 0 to t ICT dt plus initial voltage. Okay. So the current is given over here. So I'll find out the V1t first. The capacitor is 12 micro. Micro will go up. This is 0 to t. ICT is given 30 e to the power minus 2t and it is in ampere or milliampere. This is in milliampere. So you can take 10 to the power minus 3 out. Is it okay to you? Now this is gt plus the initial value. the initial value is given is 50 volt. Okay. Now you have to solve this equation. Directly we are getting the V1T over here. Okay. I'll solve this integration for you actually. So 10 to the power minus 3 into 10 to the power 6, it will be 10 to the power 3 divided by 12. This 30 can come out, this one. And if you'll integrate this, is it okay? This integration will be minus 2t. Minus will come out and divide by 2. Okay. 0 to t plus 50 as it is. Now you can solve this and you will get V1T is nothing but minus 1250 e to the power minus 2t plus 1300 volt. This is the value of voltage across this capacitor. Directly you are finding this. Now to find out the voltage across this will be very interesting. Across this 40. See, the voltage V2 is given across this point, means across this point, right? Here, this is the voltage V2, correct? Okay. So friends, you have to calculate the voltage V2 given across this point. So, across this point, the situation is like, can I resolve the situation like 12 microfarad is given? This is the voltage V2. Over here, I can resolve this. These two capacitors are connected in parallel combination, so I can resolve them. 20 and 40, they are connected in parallel combination. It means simply you can add them. This is the 60 micro, and here the current is as it is given 30 e to the power minus 2t. Okay. Now the current in this also the same, 30 e to the power minus 2t. So now the calculation is remain for V2. This is nothing but 1 by C. 1 by 60 micro, 10 to the power 6 will come up and 0 to t. The current is 30 into e to the power minus 2t dt plus initial voltage. Okay. The initial V2 is given as the 20. Okay. So this is again equation. Now solve this equation, and if you solve this equation, you will get minus 250 e to the power minus 2t plus 270 volt. This is V2. Now he was asking for V1 and V2. The first part of the question is completed. V1 we completed, we get already, and this is the V2. Now come to the second part of the question. He is saying the energy in the each capacitor at t equal to 0.5 second. T equal to 0.5 second. Now energy in the capacitor is half CV square. As you know, half CV square. You are having half, you are having the value of different capacitors. Now the question is, what is the voltage? Now he is asking for what? The energy in each capacitor at this. Each capacitor. Here the C is given for this capacitor. You need the voltage. For this capacitor, you need the voltage at t equal to 0.5 second. Now, suppose you want to find out the value of Vt at 0.5 seconds. So my question is, can you find out? Yes. Vt is given. Instead of t, you have to put 0.5 in the equation, minus 250 e to the power minus 2 into 0.2 plus 270 like that. You will get some value, constant value. That value you will put over here in the energy formula. So you can get E1, E2, E3. This is all about this question. I hope this is clear to you. Now, come to the second part. In the second part, this is the question and the circuit is there. This is the second question and the circuit is given over here. Find Vc, IL and the energy stored in the capacitor and inductor in the circuit given in the figure under DC condition. Please observe this. Here they mention the DC condition. DC condition, omega equal to 0. For the DC condition, I told you the capacitor behaves like open circuit. The capacitor behaves open circuit. Inductors behaves short circuit. So wherever you have inductor in the circuit, you can replace by short circuit, and wherever you have the capacitors, you can replace by the open circuit. So in this entire circuit, we can do these things, And the question is, find the VC. Where is the VC? Here is the VC. IL, where is the IL? IL is given over here. And the energy stored in the capacitor and inductor is asking for the energy stored also under DC condition. So I'll replace the circuit by DC condition given in the question. Okay, I'm doing this over here. This is the 6 ampere. Fine. Connected with 4 ohm, 2 ohm. I'm replacing capacitor by open circuit. This is 5 ohm. I'm replacing the inductor by short circuit, and the current over here is IL. The voltage across this is VC. Okay, this is short circuited, and everything remains same. You can see over here. Now the question is simply circuit. You can do it by nodal analysis, mesh analysis, whatever you want. Okay. I'll do it by nodal analysis. Okay. This is one node. I grounded it. This is node. Assume this 1 and this voltage is V1. This node is grounded. So we are having only 2 nodes. This is the open circuit, open branch. No current will go this side, and this is the dead branch, I can say. Is that okay? Here I have to apply the nodal analysis. V1 divided by 4 minus 6 is coming. Fine. Now here V1, this part is connected to this 0 directly. V1 minus 0 divided by 2. One node, 3 branches connected. 3 terms are coming in the equation equal to 0. Okay. So this is 4 V1 minus 24 plus 2V1 equal to 0. So 3V1 equal to 24 and V1 equal to 8 volt. V1 equal to 8 volt. This is the 8 volt. Now if this is the 8 volt, you can get the current in this side. The current in this is 2 by 8 means 4 ampere. This 4 ampere current is coming to this side. So it means you calculated the IL. IL is nothing but the 4 ampere. Is it okay to you? Now come to the VL. This is the VL over here. Can you find out? Yes, you can find out. See, what is the value of current in this branch? 8 by 4. It means 2 ampere. 2 ampere is the current over here. 4 ampere is the current over here. You need to calculate the VL. Can you apply the KVL? Wait a minute. Let me clear it first. Wait. Your task is to calculate VL now. So everything I'll remove. Your task is to calculate VL. This equation will go out. Please remember this. V1 is nothing but the 8 volt. Okay. Now come to the question. And the question is, we have to find out the VL. Here the current, this is the 2, current is 4 ampere, fine. Here is the current is 2 ampere, here is the 4 ampere. Now I'll apply the KVL in this. So, okay. This is the mesh kind of thing. Imaginary, though this is the open, but in the open circuit, we can find out the voltage, because voltage can exist in the open terminal A and B. Here the voltage is something. Okay. In your household, you are having 2 pins like this, and you are having 230 voltage there. Okay. Anytime you can connect this in the outer circuit, and you can get the current from this. So here also, though this is the open, we are having the voltage VL over here. So I'll start with the KVL from the point A, and I'll come back to the point A. So here I'm getting 4 into 2, 8 volt negative. This is the negative. Come to here, minus VL I'm getting, VL. Is there any current in 5? No. So the voltage drop across 5 is 0. Come to this. Here I'm getting plus minus 4 to the 8 volt. So here 8 volt equal to 0. This 8 and this will, this 8 will cancel out, and the VL is nothing but the 0 volt. So the second question, the VC. DC is the 0 volt. This is 0 volt and this IL is the 4 ampere. Okay. Now come to the second part of the question. And in the second part they are saying find the energy stored in the capacitor. So energy stored in the capacitor, you know the formula, 1 by 2 CV square. 1 by 2, what is the capacitance given? This is the 2 Faraday. The voltage is 0. So this is the 0 joule. This is the energy in the capacitor. Now come to the energy part of the inductor. The energy of the inductor is half Li square. Half Li square. Half, what is the value of L given over here? 0.5 given. And what is the I? I you calculated 4 square. Okay. So this is 1 by 4 into 4 square. So finally you are having 4 joule energy. Okay. In the inductor you are having 4 joule energy. In the capacitor you don't have any energy because the voltage across the capacitor is given 0 volt and current across the inductor we have 4 ampere. So the energy in the inductor is 4 joule and the energy in the capacitor is 0. Okay. I hope it's pretty clear to you. In the first question we simply use the voltage equation of the capacitor equation of the voltage, right? In the second one we use the DC condition. Now we know the reactive capacitance, we know the inductive reactance and inductive reactance and capacitive reactance. So for the DC condition we know the formula. So we applied in this and got the answer. So this is all about the problems. Now come to the next one. The problem is given under steady state DC conditions. Under steady state DC condition, find I and V in the circuit. The circuit is given over here. Now under DC condition at the steady state we have to find out something, right? Okay, fine. So the condition is given is the DC condition. Again for the DC condition the capacitor is nothing but the infinity and the XL is given as 0. This is short circuit and this is open circuit. So replace it, please replace it. So your resultant circuit is, this is 10 milliampere connected with 30 kilo parallel. Okay, fine. This is short circuited, open circuited, and this is 20k. Okay. Now we have to calculate the current. They're asking for the current I, and they're asking for the V. Where is the V? V is over here. V is over here. Now the 10 milliampere current is coming, and here the current is getting two parallel connected elements, 30k and 20k. Can I apply here the current division rule? Yes, I can apply. I need to get the current in 20k, I 20k. So formula is, this is I, okay. Formula is the main supply current 10 milli multiply with the opposite branch resistance 30k divided by summation. This is the 50k. K will cancel out, and this will be 5 2s are 2 3s are 6 milliampere. 6 milliampere is the current. 6 milliampere is the current. This. Now come to the V portion. This portion. Now in this, if 6 millicurrent is coming over here, so you need to find out the V. What is the V now? Tell me. V is nothing but the current into resistance, right? So the V is nothing but 6 milli into 20k, right? So this is nothing but 120 volt. Okay. Is it okay to you? So your answers are I is nothing but 6 milli and volt is nothing but 120. This is all about this. Capacitors and inductors, how they behave in DC situation. Okay. Now the initial condition, we discussed it, initial and steady state conditions. Keep in mind that the capacitor voltage is always continuous, so that V0 is nothing but the V0 minus. Continuous means they will not change abruptly. As we discussed, at t equal to 0, suppose we are switching. We are closing the switch. This is the t equal to 0 minus. This is t equal to 0 plus. So if the condition of voltage across the capacitor is Vc0 minus, the same will be there in 0 plus also. See, that's why I'm saying the voltage across the capacitor is always continuous. Now, similarly, across the inductor, the current is always continuous. So for the inductor also, if here in this region 0 minus, at the 0 plus, up to 0 plus, current will not change. Means if you are having 5 ampere current initially, after switching also, up to 0 plus time, it will be 5 ampere only. Okay. So here, please observe this point. At t equal to 0 minus, 0 minus is just before the t equal to 0. Denotes the time just before a switching event, and t0 plus is the time just after the switching event. Assume that the switching event takes place at t equal to 0. If switching takes place at t equal to 0, so t0 plus is the positive this region, and t equal to 0 minus is the left region. This is the right and left. I hope this concept is clear to you. So based on this, come to the initial condition problem. This is the proper problem which will be there in the GATE exam also. The switch in the figure has been closed for a long time. For a long time the switch is closed means the circuit was operated in a steady state. Steady state. Initially the circuit was in steady state. Steady state, I told you, if circuit is being there for a long time, so you can say it is in steady state. Okay. So which steady state? Minus infinity, infinity. This one. The circuit is in this region, minus steady state. Why? Because at t equal to 0, you will change something, you will switch something, and after a long time from the switching, again it will become in a steady state condition. So the initial steady condition is given, steady state condition is given for minus infinity, right? So please observe this question. What he is saying, the switch has been closed for a long time, it is open at t equal to 0. Okay. At t equal to 0 will open the switch. Now we have to find I0 plus V0 plus. In the second question we have to find I0 plus di0 plus by dt, dv0 plus by dt, and I infinity v infinity. Okay. So I'll come to the proper circuit diagram. Okay. The circuit is saying, this circuit is saying the switch has been closed for a long time. The initial condition is like this. The circuit is closed. The circuit is closed for a long time. Now the circuit is closed. So your circuit will be, this is 12 volt. This is your inductor. We have to replace inductor by something. Here I am leaving inductor as it is. This is the switch over here. This is the capacitor. I'm leaving this capacitor because later I'm coming to the condition of capacitor and inductors. Don't worry about that. So see, it was in steady state, right? Means minus infinity. At t equal to minus infinity it was working. Minus infinity it was working. T equal to infinity means A is equal to 0. Is it okay? So if A is equal to 0, what about the Kc? XC means capacitive reactance 1 by SC, so it is infinity. What about inductive reactance? This is SL means 0. So you will replace the inductor by short circuit. You will replace the capacitor by open circuit. This is the as simple as that. You can see this. The circuit was, working in the steady state. Steady state, I told you, t equal to minus infinity. If t is the infinity, S is 0. If S is 0, you know the formula. So you can get the reactance. Capacitive reactance is nothing but the open circuit. I opened it. Inductive reactance, it is the short circuit, I shorted it. Everything remains same. Okay. This is about V0 I can say, or 0 minus I can say. Here's the current I0 minus I can say. Minus means before switching. This condition is before switching. Switching, you can open the switch or you can close the switch. So in the first part, we'll find out this, because if you can find out the I0 0 minus and V0 minus, so you know about the inductor I0 minus is nothing but I0 plus. You know for the capacitor V0 minus is nothing but V0 plus. Okay. So come now here, this is the very simple circuit. This is the open. Total resistance is 6, 12 by 6. This is 2 ampere. 2 ampere current will flow over here. So I0 minus is 2 ampere. The same current will be I0 plus also. So here the current is 2 ampere. Now come to the V0 minus. The voltage across this 2 volt is nothing but the V0 minus. Here the current is 2. So this is plus minus 4 volt. The value of this is nothing but 4 volt. Is it okay? So this part of the question is finished. Now these 2 parts we'll do in the next video lecture. So I hope the concept is clear to you. Okay, and you can try at your home also. This Ti0 minus, and this is the derivative part also. Okay, you can apply something over here and you will get. If you will not get, I'll clear the doubts in, I will clear this concept in the next video. So we'll meet again, friends. Till then, take care and bye.